Hello, water managers. My name is Matt Fleming. I am part of the Water Management Systems Division here at the Hydrologic Engineering Center, and this is the last video in the HEC-HMS Real-Time Hydrologic Modeling series. In this presentation, we're going to talk about key parameters, key HEC-HMS parameters for real-time forecasting. So let's start on this slide. This slide on the left, you should see a plot of a hydrograph. Again, the blue line here is the computed results from an HMS simulation. The black line is the observed flow, and you'll notice that the observed flow stops at the time of forecast. We ran out of observations, and now after the time of forecast, this vertical line here, we're using the model to predict the runoff given a forecast of precipitation. And what I have on the right side is a summary table showing the metrics or statistics from the simulation. You'll notice in this panel right here, we have computed results. So you should see things like peak discharge, the total runoff volume here. And then this bottom panel, this shows you observed flow information. So the peak discharge from the observed flow hydrograph, the volume from the observed flow, and then some metrics. Common metrics that you see in hydrologic simulation are things like Nash-Sutcliffe efficiency score. So a score of 1 is a perfect result. Your simulated results match exactly the observations. Values from 0.7 to 0.1 are really good. That shows the model is doing a good job predicting or simulating the observation. Values from 0.5 to 0.7 are fair, in my opinion, and if you have a Nash-Sutcliffe below 0.5, you should definitely spend more time calibrating the model. The other metric that I really look at is the percent bias in volume. And what that means is how close are you to the total runoff volume? And in this case, you have to be careful with using a forecast and looking at volume, because typically when you do a SWMS forecast, you run out of observations in the forecast period. And so it's going to look a little off if you just compare the volume here of runoff from your computed results to your observed results. And what the percent bias does, though, it compares the volume only during time steps when you have observations and simulated results. And in this case, we want a percent bias that's 0%. That means there is no bias in the runoff volume. If your bias is plus or minus 5%, within plus or minus 5%, that's a pretty good result. If you're over 10%, then you should probably spend more time adjusting key parameters to get that bias, volume bias below 10%. All right, so this is the most important slide of this talk. This lays out key parameters, and these parameters are really for most SWMS watersheds. Typically use the deficit and constant loss method, the Maud-Clark transform method, linear reservoir base flow or recession base flow, and then certain routing methods like Maud-Poles, Muskingum, and Muskingum-Kunj. And the way I broke this out is your initial conditions. For initial conditions, there are HMS tools that you can use to set those initial conditions using observed information. For example, there's a base flow editor within the forecast toolkit that allows you to select a gauge, and then you can use the flow at that gauge in a ratio to set the initial base flow at different subbasin elements. And this is a real quick way to come up with setting that initial base flow so you don't have to manually type initial conditions for every subbasin in the basin model. Same thing for your reservoir elements. You can set the initial reservoir elevation or storage using a gauge, a time series of observed elevation or storage. And then for your initial SWE and snow cold content, there are data products and Cumulus that you can download in the extract list, and then link those to your HMS model and use that information to set the initial snow water equivalent and cold content. So that leaves you really the initial moisture deficit as a initial condition that you need to set for every forecast alternative or every forecast simulation. And this initial moisture deficit, it is really dependent on the conditions of the watershed at the beginning of the simulation. So you can't use an initial moisture deficit from an event that happened 2 weeks ago or 2 years ago. Really, you need to customize the initial moisture deficit for the conditions of the watershed at the beginning of the simulation. More than likely, once you do forecasting over a couple of events, you're going to get a good idea for what the moisture deficit is going to be for different conditions. As you transition from a dry watershed to saturated, you'll get an idea for, is the deficit 1 inch? Does it need to rain 1 inch before you see runoff, or does it need to rain 0.25 inches before you see runoff? So those are initial conditions. Process parameters, if you do have snow, then you need to adjust your PX temperature and your wet melt rate when you calibrate your model. More than likely, you're using the deficit constant method, and you're going to hone in on that constant loss rate. The constant loss rate, it's a parameter that impacts both the peak flow and the volume. So if you're trying to match the peak flow of your observed hydrograph in the look-back period, you can decrease that constant loss rate to generate larger peak flows, or you can increase that constant loss rate to decrease the simulated peak flow runoff from the subbasin element. So that's going to be a really impactful parameter. If you're using the recession base flow method, then you're going to adjust the ratio to peak or the recession constant parameter. If you're using the linear reservoir base flow method, then really the parameters that you would adjust are those fraction parameters, groundwater 1 fraction and groundwater 2 fraction. But again, what I found is for these parameters, they're seasonally consistent. So if you're within a typical season, out west, here we have a rainy season from October through March, and I would expect that that groundwater fraction is somewhat consistent during that period. Once the watershed has reached a saturated state, then those fractions are going to be consistent during that period. So those are parameters that I would recommend that you adjust every time you're doing a calibration. And then the parameters on the right side are those parameters that you would occasionally adjust. If you have time, if the model is just not performing the way that you need it to, you want to get your Nash Sutcliffe to at least 0.7 or your percent bias below 10%, then you could consider adjusting these parameters as well. The dry melt rate function, if you're doing a long-term simulation and you're trying to match the melt of the snowpack as the watershed transitions from spring to summer, then definitely adjust the dry melt rate function. The reason you would adjust your mod Clark or Clark time of concentration and the storage coefficient is, again, if you're simulating conditions that are outside of the bounds of when the model was originally calibrated. Right, so maybe the time of concentration, the storage coefficient, those values were set simulating a large event, but you're trying to simulate a rather average event. So in that case, you might need to increase your time of concentration because you don't have as much water sitting on the watershed, so the travel times will be longer, and you might need to increase your storage coefficient. Reach routing. Typically, I don't adjust the number of sub-reaches for mod poles. That has just minimal impacts on the results. If you do adjust Muskingum K and X, those can be very impactful. But again, you're going to get a feel for those values as you get an idea for how the reaches respond under different conditions. If you have high flows, you would expect different K values, different lag values versus low flow K values. And then if you really need to, you can adjust your Muskingum-Kunj, Manning's N value, and the energy slope. Crop coefficient, I would not really suggest adjusting that parameter, but if you're doing a longer term simulation and you're trying to match evaporation or evapotranspiration over multiple months, and you're just not able to reproduce the runoff response, then consider adjusting the canopy crop coefficient. And then finally, if you do need to increase your evapotranspiration for a longer term simulation, so again, if you're looking at a couple of months, then you can adjust your monthly evapotranspiration rate or the ET coefficient within the Hammond evapotranspiration method. All right, so if you have any further questions, these are references on this page. I would really recommend looking at the SWMS user manual documentation. That page here, the second bullet, will direct you to the HMS user manual documentation page, and within the HMS user manual documentation page, you can go, there's an additional link to other options under HMS, and you can see tutorials and guides. Also, I would direct you to the discourse page, and then also the team site where you can ask any questions that you have on the topic of using HMS for your flood forecasting. All right, hope that helps, and thank you for your time.